Quick, what weighs more, 10 pounds of feathers or 10 pounds of bricks? Okay, bit of a trick question. 10 pounds of bricks and 10 pounds of feathers weigh exactly the same thing. The reason we're used to thinking of bricks as being heavier is because they're more dense. So one brick might weigh 10 pounds, but I would need a huge garbage bag, probably several garbage bags filled with feathers in order to get 10 pounds of feathers. So really, when we're talking about these two different objects, we have this conception in our head of what's heavy. What really we want to pay attention to is density. We define density as the mass per unit volume of a substance. So if I measure an object's volume, I take its mass divided by that volume, I get the density. And we're going to use the symbol rho for density. It's the Greek letter rho. It looks kind of like a P, but it's actually a Greek letter. That will be our symbol for density. And just working out the units here, we can see that since it's mass over volume, the units should be kilograms per meter cubed. To give you an idea of how density works, we're going to consider the densities of some common materials. So let's start off here. Let's look at helium, a very light material. You know, if you put it in a balloon, helium goes up, it floats on air. Helium has a very, very light density. It's about 0.166 kilograms per meter cubed. So one of the reasons it floats on air, because it's less dense than air. Air has a density of about 1 kilogram, 1.27 kilograms per meter cubed. So if you imagine a square meter cubed, so about yay tall, about yay wide, probably about the size of a bathtub. 1 meter cubed, that would only be 1 kilogram, so about 2 pounds worth of material if I weighed all of the air in a square cubic box. Then we jump up to liquids. So for example, oil is about 900 kilograms per meter cubed. So we know oil is much more dense, about 900 times more dense than air. But it's slightly less dense than water. So if I take the same cubic meter and I fill it with water, water would be about 1,000 kilograms per meter cubed. So water is a little bit more dense than oil. This is why oil will float on water. They say that blood is thicker than water. In fact, that's the case. Blood has a density of about 1,060 kilograms per meter cubed, so slightly more dense than water is. We could go on to other materials. I've only put a small list of things here, mostly either gases or liquids. We could also consider denser materials. So for example, lead is usually thought of as being a very dense material. It can stop Superman from seeing through it, so it's got that going on for it. But it's very dense. Its density is roughly 11,000 kilograms per meter cubed. However, you might think that all solids are denser than all liquids. That's not necessarily the case, because if I look at mercury, which is a liquid, at room temperature and pressure, it's about 13,000 kilograms per meters cubed. So it's a little more dense than lead. So if I take some lead and I put it in mercury, the lead would actually float. However, neither of these two materials have anything on neutrons. So if I were to look at a neutron star, which is a special type of star composed entirely of neutrons, its density is 3 times 10 to the 17. 10 to the 17, 13,000 is about 10 to the 4. So we're looking at a difference of about 13 orders of magnitude. Or to put that another way, the neutron star is about 10 trillion times more dense than mercury or lead. Let's try putting that in even another way. So let's say you were to get a teaspoon of a neutron star. Just take a spoon, go onto a neutron star, scoop up some neutron star. That teaspoon of neutron star would weigh more than all of humanity combined. You might have heard someone say, well, that's just the tip of the iceberg. And the reason is, if you look at an iceberg, the vast majority of it is underwater. Ice floats. But if you are the Titanic heading towards what you think is just a small piece of ice, the chances are you should probably steer away because there's going to be a lot more ice underneath. The reason is that the density of ice is pretty close to the density of water. They're not orders of magnitude different. Ice is about 934 kilograms per meter cubed. Water is 1,000 kilograms per meter cubed. So we have just a little bit sticking above. Most of it is down underneath. To figure out why this is the case, we need to figure out why do less dense objects float. Let's see what happens when I try to submerge an object in water. So here I have a tennis ball. Let's say I want to take a tennis ball and try to submerge it in water. Well, gravity is always trying to pull the tennis ball down. So the tennis ball will want to go down. Not too surprising there. Go with my tennis ball, gravity pulls it down. However, the tricky part with a fluid is that as soon as the tennis ball goes down, the height of the water doesn't stay the same. Water needs to go somewhere. I can't just put the tennis ball here because there was water there, and that water needs to go somewhere. In the case of submerging a tennis ball, the only place it can go is up. So I've raised the height of the water here. So if we take on principle that gravity is pulling more massive objects down with greater force, then whether an object floats or sinks isn't a matter of just looking at the mass of the object. So it's not just the matter of the mass of the tennis ball. I also have to consider the water. How much water is getting brought up in its place? If the tennis ball were more massive than the water, it would sink down. However, if the water that the tennis ball displaced is more massive, the water would go down, the tennis ball would rise up, and it would float. Let's say I take the object I'm trying to submerge and I place it on a balance. And on the other end of the balance, I place the amount of water that I'm trying to displace, the amount of water that gets pushed up because I'm submerging my object. Well, if the amount of water I am trying to displace is more massive than the object, then the water is going to sink and the object is going to rise up. However, if the object is more massive than the water I'm trying to displace, the object would sink and the water displaced would go. It's just a matter of density. Which of them is going to have more mass? And it's going to depend on the density of the object and how much I submerge it. So if I want to know the mass of the water displaced, that's going to be equal to the density of the water times the volume displaced. That is how much water is being displaced. If that is bigger than the mass of my object, then the water is going to go down and the object is going to float up. What we've been talking about is the force of buoyancy, or the buoyant force. In order to figure out how big that force is, we need to know how much fluid we've displaced. So we're going to measure the volume displaced. The amount of fluid that gets displaced. Basically, it's how much volume, how much fluid has to rise up in order for the object to be submerged. So it could be that I submerge my tennis ball entirely in my fluid, and then the amount of water that has to rise up is just the same as the volume of the tennis ball. However, I don't have to push the tennis ball all the way underwater. It does not have to be the entire volume of the tennis ball, because if I only push this much of the tennis ball underwater, if only half of it is submerged beneath the water, then my volume displaced is just half the volume of the tennis ball. So it's however much of the object, however much volume of the object is underwater. So when I have an object submerged underwater, we can see there are two forces on it. One force is just the gravitational force that pulls it down. But there is also a buoyant force that pulls up on it. And it's going to be pulled or pushed up with a force that's just related to the amount of water that we're displacing. So that buoyant force can be written as the density of whatever fluid I'm in. Could be water, could be oil, even gases count as fluids in the physics world. So whatever fluid I happen to be in, times the volume displaced, so that gives me the mass I'm displaced. And since it's gravity that is pulling the water down, I just have to put my gravitational field in here. This is my buoyant force. It's the density of the fluid times the volume displaced times the acceleration of gravity with gravitational field equivalent. Now, if you've ever been tubing, or just in those little floaties that they put on little kids so they don't drown, you know the buoyant force can be quite large. If you try to take those inner tubes or some sort of floaty device and try to force it to go underwater, it takes a lot of force to push down on it. Well, the reason is, it's not necessarily that you are pushing this balloon down, it's that you're pushing the water up while you're doing it. Again, it's just a matter of water displacement. When you push something under the water, you've got to push the water up because it has to go somewhere. If that model of buoyancy is correct, we should be able to test it. So that's what we're going to do here. I have here a 273 gram brass weight. I have a force meter here, which we're measuring the force on here using this computer. We can see if this force meter is measuring things correctly, then this 273 gram weight should give a force of about 2.6 newtons. And you can see, at least within experimental uncertainty, that's about 2.6 newtons. You get that just by taking into account that the force of gravity is pulling down, the tension on the string is pulling up, that's what we're measuring, and just taking m times g, 9.8 meters per second squared, you get about 2.6 newtons. Now, it should be true that when I submerge this brass cube in the water, the force should go down because there's got to be some buoyancy force pushing up. Plunging the cube underwater, we simultaneously cause some of the water to rise up. In order to raise that water up, there's going to be some force that does that. That's the reaction force to the buoyancy pushing up on the cube. Let's just submerge this cube all the way. And we should be able to see over here, now the tension is reading about 2.3 rather than 2.6, at least within experimental uncertainty. The last few digits are going to bounce around a little bit just because there's some air currents that are going to be affecting the string as it moves up and down. There's some uncertainty associated with that. But you can see we're about at 2.3 newtons of force. So let's see whether our math works out on this or not. So I've got my cube, it's submerged in water. I've already done my free body diagram. I can see there's three forces on my cube. There's the force of gravity pulling it down. There's a buoyant force that's pushing it up. And there's also some tension that's pushing it up. Now, if we've done this correctly, it should be true that the tension force I am about to calculate is equal to the 2.3 newtons that we measured on our computer screen over there. So let's see. We've done our free body diagram. Next, we are going to sum up the forces. Summing all the forces on the cube, we can see that we have a tension force pointing up. We've got a force of buoyancy also pointing up. And we have a force of gravity pulling the cube down. This has to equal the mass times the acceleration by Newton's second law. but we know the cube is just stationary, it's not accelerating. So my acceleration is 0, so both side is 0. Let's plug in the formula for our buoyant force. We know that's the density of the fluid times G times the volume displaced. Similarly, I can plug in the formula for the force of gravity. Now, all of my measured quantities are given over here. I'm taking the liberty of measuring the mass, the gravitational acceleration, we know that. The density of water is about 1,000 kilograms per meter cubed. And the volume of the cube, which you can get just by measuring the lengths of the side and then taking length times width times height, is about 32.8 centimeters cubed. I've tried to put some uncertainty on those. So let's say this will give us tension minus, or plus rather, fluid density times G times the volume minus mg must be 0. We can solve for the tension by moving these two over to the other side. I'm just going to add mg to both sides and subtract rho gv. It's going to be mg minus rho gv. When I plug these numbers in, what we will see, let's see, that's 273 grams. This is 9.8 meters per second squared. The density we said was 1,000 kilograms per meter cubed. G is again 9.8 meters per second squared. And the volume is 32.8 centimeters cubed. Now, you will need to do some conversions for this, or you could just plug these numbers directly into Google's search bar, and Google will do the conversions for you. But lo and behold, when you do this, you will get just what we found. T is about 2.3 newtons. We could put some uncertainty on there if we want, but I'm being a little bit conservative here. 2.3 newtons. Certainly there's no difference between what we observed over there and what we calculated over here. No experimental difference within the uncertainty. So what did we show? We showed that if we use this formula for the buoyant force, we can pretty accurately measure how much the water is pushing up on the cube. So this must be a good model for how the buoyancy force works. So we know an object will sink if it is more dense than the fluid it's submerged in, and it will float if it is less dense than the fluid it's submerged in. We can use this principle to build all sorts of neat things: boats, hot air balloons, submarines. In fact, there's a simple little toy you can build. What I have here is basically just a water jug with a pipette tube in it. And the pipette tube is floating because it's got some air in it. But if I add some pressure to compress the size of that air, we can see I can get my pipette tube to go up and down. What's going on is by increasing the pressure when I squeeze the bottle, I'm compressing that air, I'm making it more dense, more water is seeping into the pipette tube, and that is a big enough density change so that I can make the pipette tube more or less dense than water so that I can get it to float or sink at will. Let's test what you've learned so far. So let's say you are off in outer space where there's no gravity, and you're in a rocket ship, and you fill a room of the rocket ship, you fill it with water. Then, in that water, you place a floating, some sort of floating inner tube. And the inner tube is filled with air, so it is less dense than the water is. What's going to happen to the inner tube? Is it going to rise up, fall down to the bottom, stay where it is, what's going to happen? All right, let's see if we can figure out what's going on. So I know I have a formula for the buoyant force. The formula says you've got the density of the fluid times the gravitational field, the acceleration of gravity, times the volume of fluid displaced. Now the density of fluid is just going to be the density of the water. The volume displaced, since my inner tube is just submerged entirely under the water, it will just be equal to the volume of the inner tube. The problem comes when I try to figure out g. Normally, we're used to thinking of g as a constant. But we're in outer space. There is no gravity here. So my g is 0. Therefore, my buoyant force has also got to be 0. So there is no force pulling up. There is also no force pushing down, because gravity is not there anymore. So wherever I place my inner tube, it's just going to stay there. Now, it's not going to float up, it's not going to float down. It might be a little bit difficult to conceptualize this, because we're used to thinking of, when we have an inner tube or a floaty or something less dense than water, we're used to thinking that it rises up. However, there's a problem with that very definition. Right? If we're in outer space, how do we know which direction is up? If I'm on the Earth, I know down is the direction that the Earth is. But if I'm nowhere around any other objects, what is up and down? All of a sudden, up and down start to lose their meaning. It's easy to visualize the force between two solids, right? I have a piece of paper, I can exert a force on the paper and get the paper to accelerate. It turns out fluids can also exert force, but in some sense it's more difficult to visualize what that force looks like. So right now, I am being bombarded with air molecules. They're constantly banging into me, and every time they bang into me, they exert some force on me. So any object surrounded by any fluid is going to feel some amount of force. Well, if it's feeling a force, why doesn't it start to accelerate? It doesn't accelerate because it feels an equal and opposite force on the other side from the fluid on the other side. In fact, it's going to feel a force from the fluid on all possible sides. Now, I've drawn a pretty simple shape here, just a cube. And the sides of a cube, the area of each side of the cube is identical to the other sides. So it's not going to feel any imbalance in force. It's going to have the same number of molecules pushing on every side. And it turns out most objects have that property, even if they're irregular shapes. But what is true is that if I were to have a bigger side, if I were to have, say for example, a bigger cube, I would have more air molecules banging into me. And therefore, we would have more force. Well, that makes force a little bit of a difficult quantity to work with, right? We don't want something that is going to give me a different physical quantity every time I just change the size of the object. We'd like something that would work for objects of all sizes. And that's why people came up with this idea of pressure. So rather than worrying about the force on the object, which can change as I get a bigger object, I'll draw my bigger cube over here. I have 3 force arrows on it. 3 from the other side just to balance out. Rather than dealing with force, which we have to then be concerned about the size of the object, we're going to take the force per unit area. And we define this as the pressure. That's the pressure of the fluid. Now, the units of pressure, since it's just force over area, we would say that the units are going to be force is in newtons, area is in meters squared, So the force is just going to be newtons per meter squared. And since Pascal had a lot to deal with pressure, we give the unit also, we renamed that unit the Pascal, just to give it a little bit of a nickname. Newtons per meter squared is sometimes a mouthful. The units of pressure are pascals, which is the same thing as a newton per meter squared. Now, one helpful way to remember that, there's a story that goes like this. We had Newton, we had Pascal, and Gauss, another famous physicist slash mathematician. And these guys were all playing hide and go seek, and Gauss was it. Gauss closed his eyes and he started counting, and Pascal went off and he went to go hide. But Newton stayed in one spot. And what he did was he crouched down and he drew a box around himself. The box was 1 meter on its side. And so Gauss kept counting, and then eventually he looked up and he said, "Newton, I found you." And then Newton said, "No, you found Pascal." Because it's 1 Newton per meter squared. There is literally pressure all around us. About 2,000 pounds of pressure for every square foot of your body. So air pressure, 1 atmospheric pressure, is an incredibly large amount of pressure. And that's a little bit difficult to conceptualize because I don't feel myself getting crushed by 2,000 pounds for every square foot of my body. So why is that not happening? Well, it turns out I also have internal pressure that's pushing out just as much as the 2,000 pounds of atmospheric pressure is pushing in. But if we create an imbalance in that pressure, we can see pretty catastrophic results. So here I have a beaker filled with room temperature water, fairly cold water. And here I have a hot plate with a soda can on top where I'm boiling water out of the soda can. So I've got maybe about ½ an inch of water at the bottom of the can. Might be a little bit difficult to see, but there's some steam coming out. So what happens when I am boiling this water is the water turns to steam. It pushes some of the air that was in the can out. So if I were to cool this can off very quickly and not let any of the air escape, the steam inside would condense back into water. And when that happens, I will create a pressure imbalance. Let's see what happens when I cool this can off by dumping it in the cold water. I'm just going to flip it upside down really fast in the cold water. Grab it. Oh, we can see we create a pretty large pressure imbalance. So my can is very, very crushed now. So I mentioned that atmospheric pressure is all around us. How big is atmospheric pressure? Well, it turns out atmospheric pressure, if you're in chemistry class, you would say it is 1 atmosphere, which is true. It is 1 atmosphere. In physics, since we're working with units of pascals, we want to be able to convert atmospheres to pascals. It turns out that 1 atmosphere is about 101,325 pascals, or equivalently, it's about 10 to the 5 pascals. So it's about 100,000 pascals. 100,000 is a pretty big number. So that's 100,000 newtons for every meter squared of area that you have. That is a lot of pressure. And that pressure is pushing on me all the time. So let's put that number into context. 100,000 pascals. Well, the area of my body is about, we'll say 2 meters squared of area, which would mean, using my definition of pressure and solving for the force would just be the pressure times the area, which would mean my force is about 200,000 isn't a unit that most students, at least most American students, will have had a whole lot of experience with. So again, let's put that into context. That's about 50,000 pounds of force that is pushing on your body right now, just because air molecules happen to be hitting you. Let's try another example to test what you've learned so far. So let's say you're driving a car, and all of a sudden, you hit the accelerator. So you're slamming on the gas, you can feel yourself start to go backwards. What's going to happen to the helium balloon? Is it going to move forward, stay in one spot, or move to the back of the car? Again, slamming on the gas, your car accelerates forward. Does your helium balloon move to the front of the car, stay in one spot, or move to the back of the car? The answer to this riddle just comes from Newton's laws. It has to deal with inertia. We know that more massive objects are less likely to accelerate. They accelerate less than a smaller object pushed with the same force. So here, I have helium floating. Now you might think that much like any other solid object, the balloon is going to get pushed to the back of the car. However, the balloon plus the helium is less dense than the air inside, which means that air is going to rush to the back of the car because it's more massive, it has more inertia, it's less likely to accelerate with the car. It's going to get pushed to the back while the helium balloon moves to the front of the car as you accelerate that way. The helium balloon moves with the acceleration.